I'll give everyone a few minutes to trickle in, probably 2 or 3. I'll wait about a minute and a half more. Oh, and does anyone have any questions?
I just have a quick question regarding how to submit the homework. I know you had said you were going to send out an email about the application information. I don't know if I just missed the email or.
Thank you for reminding me. So I need to send out an email about that. And I also need to create a submission folder on Blackboard. So to do for me.
Thank you.
Thanks for the reminder. Create Blackboard submission. And send instructions. Good. Any other questions? Okay, so let's get started. So I was way too formal last time, and I've sort of dug myself into a hole because I've already set a homework, which means that I do need to teach you how to solve those problems. Starting from next week, we'll primarily be computing integrals, and they're sort of difficult to screw that up by being too formal because after all, it's a computation. And no matter how you slice it, that's a pun for what we'll be doing today. The computation goes the same way. But today, the problems are a bit peculiar to the way that I approach the material. And so I still need to guide you through those. So I'll go through the homework problems that are due, and they're due next Tuesday. And you have access to the assignments. And I sent an email about an hour and a half ago mentioning that there were some updates to the assignments. So everyone who's on my mailing list received that email, which means if you didn't receive that email, you're not on my mailing list, and you should send me an email so that I can put you on the mailing list, right? So did anyone not receive an email? Well, I mean, you might not have checked, but anyway, send me an email if you haven't. Because I'll just be reusing that mailing list instead of sending emails by Blackboard. Now, the way this lecture is going to work is that I'm going to discuss some homework problems, then I'm going to go through some material that will enable me to discuss more homework problems, and then I'll discuss the other homework problems in turn. So we're going to alternate between me giving you essentially something close to the solutions to the homework problems that you're supposed to write up, and me covering the material necessary to understand the statements of the homework problems. So I'm going to start off with some hints for the first problem. So first off, the problem, it's a problem about logarithms. And the reason that this problem is given is twofold. First off, to check that all of you know the rules for logarithms, because I don't want to run into issues later on. And second off, it's a problem that's written with the deliberately provocative word show. Problems which have the word show are problems that will require more writing. They're going to require you to convey an argument, and that's going to allow me to scrutinize the arguments. So however you write your solution up, think that you've written a solution. Think that the solution should be readable, it should be elegant, it should be presentable. I'm going to be looking for that in the solution, and I'm going to be very particular about any sort of mathematical illiteracies or problems with the write-up. And you're going to see a lot of comments when I grade them. So let's just discuss some rules about logarithms so that we're all on the same page. So first off, I'll write log A of I write by this expression, I mean logarithm base E of A, or just the natural logarithm of A. So I won't be using the notation ln. If there isn't a base, then the base is E. And E is the special base for the logarithm. It's approximately equal to 2.718182, I think. Now, logarithms have several rules about how you use them. So first off, logarithm of A times B. What is this equal to?
Is that log of A plus log of B?
Exactly. Good. So there is a general common mistake. And that's to assume that things are incorrectly linear. So for example, logarithm of A plus B does not equal to, in general, log A plus log B. Similarly, if you have trigonometric functions, such as sine A plus B does not equal to sine A plus sine B. And neither do you have similar rules for multiplication. But you do have one rule. Logarithms take multiplication to addition. And there are lots of jokes about this. There's a common one about snakes asking for a log in order to breed, and then they say, we're adders, so we need logs to multiply. You've probably heard that one. Right. Then there's the question of bases of logarithms. So what is the defining property of a logarithm? This is from Calculus A. The defining property of a logarithm is that the exponential of the logarithm gives you back the number itself. And the defining property of log base A of something, so let's say, or log base B of A, is that if you take B to this power, then you get A. And just to remind you then how the log change of base formula is derived, if we have B, that is the same as, let's say, A. A is the same as B to the power of log base A of B by definition. And then we can take B and we can write it as E to the power of log, natural logarithm, of A. then how do exponent rules behave? If I have exponents like this, what is that equal to? How does A equal both of those things? So this is the defining property of a logarithm. You can say that the definition of a logarithm is that it is the inverse function of the exponential. In calculus A, that is how I define logarithms. I discussed the notion that some functions have an inverse, and it's an inverse with respect to composition. So if you take the logarithm of the exponential or the exponential of the logarithm, it behaves in the same way as the function f of x equals x, the identity.
I meant
So-
like the, sorry, I meant like the b to the log b of a equals a, and then the a equals
thank you.
b log
That
a
is
of
a
b.
typo. That is a
Okay.
typo. Thanks. Good. I want log base b of a, right? This is log b. This is log base b of a. Good. Thank you for the correction.
Thanks.
Right. So now if I have nested exponentials like this, what's the rule? What's the exponent rule corresponding to this? How can I write it as a single exponential? Does anyone remember?
Would it just be a to the log b of a? Or no? Because I thought e to the log.
E to the log b can be written as b, right?
right,
I
yeah.
guess here I've just replaced a with b. So I can undo, you're right, I can undo this step and I can write this, but I'd rather go in a different direction. So I'd like to write this as e to the something. What's the something? So this is a general rule about exponents. If you have something like a to the b and you take this to the power of c, then that's the same as a to the power of b times c. So this is e to the logarithm base b times log base b of a. But then also a, I can write it in a different way. I can write it as the exponential of the logarithm of a. And so what I obtain by taking the logarithm of both of these sides is that the logarithm of b times the logarithm base b of a is equal to the logarithm of a. And by rearranging this, I get log base b of a is equal to logarithm of a divided by logarithm of b. And this is the log change of base formula. So this is a reminder of some properties about how exponentials behave and how logarithms behave. So for problem one, what you want to do is you want to use this formula. Bring the exponents to the front. So what you're referring to is there was a comment in the chat. If you, for example, take the logarithm of e to the x, that's x. And so, for example, technically, when we have e to the x is equal to e to the y, as we had here, we can take log of both sides. Which is the same as x, I guess, log e. and both of these are 1. So this is another property, but for the sake of the assignment, what you want to remember is you want to remember these two things, right? You want to remember that the log of a product is the sum of the logarithms, and that when you have a different base, you can convert it just to logarithm base e like this. So if you look at what the problem is, the problem has the following expression. It has the expression log base a of bc times logarithm base c of ab times the logarithm base c of ab. So it asks you to show that this expression is equal to something else. And so how do you start working with this expression? Well, you take each one of these terms and you write every single term, write everything. In terms of log A, log B, and log C. Then you do some algebra, and then you have to undo this rewriting. Or alternatively, you could start with the expression on the other side, and you could also rewrite everything in terms of log A, log B, and log C. So the challenge here is to write up your work in a way that's mathematically coherent and to do the algebra correctly. You want to show this identity with logarithms, and the reason that the problem is assigned is so that we're all on the same page and we understand how these rules work. So I think it's a good problem for in that regard. Any questions about it?
Can you go over quickly how you got like to the second to last step, the log base b? Yeah, how did you get that from the?
So
one
this
before?
step. So we started off with A, right? And we wrote A as this expression.
Mhm.
Are you following up to this point?
Yeah.
Good. Then we also wrote A in a different way. We also said that A is just e to the logarithm of A, right?
Yeah.
Now, A is equal to A. So in particular, we have e to the log b, log base b of A is equal to e to the logarithm of A. Now, what I mentioned is that you can take the logarithm of both sides of this equation, right? If
Right.
two numbers are equal, then their logarithms are also equal.
Okay. Yeah, I see now. Sorry,
And
I
what
forgot
happens
that
when
it
I
was
take the
a.
logarithm? I just get the base, exactly.
Okay.
So if you actually want to justify the algebra, the justification is take the logarithm of both sides. And that's an interesting point that I think many of you haven't seen before, but that's how you go from step A to step B. So that's nice.
Thank you.
Any more questions? Okay, so that was a review of some logarithm properties, and that covers question 1. So again, these lecture recordings are available. Has anyone in the audience tried unsuccessfully to access the lecture recordings? They should be available on Blackboard under the Zoom recordings tabs. Has anyone accessed the recording successfully? Okay, someone says it asked for a password and someone said yes. So I need to deal with the problem of it shouldn't be, it's not the intention. Oh, and I gave someone the passcode. Okay, I need to fix something then. So I will do something after this lecture. I will also send everyone the passcode. That is one thing that I will do, but I will also try and fix it. But I will send people passcodes for both of those lectures, so you'll have access to this lecture. And then you should go back to this lecture and just review this segment, and then that'll basically tell you how to do the first problem. Let's do the second problem now. Again, hints as to how you're doing it. So the second problem is a problem about algebra, about factoring, and about polynomials, and, well, just general n radicals. So you're asked to show for 0 is less than or equal to h is less than a squared. You know what's let's say by positive I mean strictly positive. So 0 less than h less than a squared. That's square roots. So this is part A of a squared plus h minus a is less than h over 2a is less than a minus the square root of a squared minus h. So how do you show something like this? Well, first off, you start with the expressions that you have and you start playing around with them and seeing what you can do with them. Now, the problem is that we have a square root. And in general, square roots are hard to work with. So going back a bit above, if we look at the common mistakes, another common mistake is that the square root of a plus b, it is not equal to the square root of a plus the square root of b. That's not the case. You're not allowed to do this. If you do this, I will scream at you on the assignments. I will put a bunch of exclamation marks and say, never do this again. And that's good. I should do that because it's important that you learn to never do this again if you do that. So, but there is a trick. There's a factorization trick. So does anyone remember from Calc A, if I have an expression like this, what can I do with it? There's a certain trick that you should have seen in Calculus A. Anyone? You multiply it by something. What do you multiply it by?
The conjugate?
Exactly. Good. And what is the conjugates? In this case, what is the conjugate?
The same thing, except instead of minus a, it's plus a.
Yes. So one thing is that I like to say is that there are only two tricks in mathematics: multiplying by 1 and adding 0. So here we're going to multiply by 1 in a clever way. We're going to multiply it by a fraction where the top and bottom are the conjugates. So it's going to be plus a. So notice that here is one of my biggest pet peeves, and I would like all of you to not do this on the assignments. If you're writing algebra, imagine that algebra is like a series of English sentences. The expressions are the nouns and the equality signs are the verbs. Every single time you write an equality, you're asserting a thought. And every single thought should have a justification. So what is the pet peeve? My pet peeve is when people just write expressions without any connecting equalities just on the page. There are multiple expressions. That's meaningless. You have to present your work like an analytical English essay. So you're saying this is equal to something. That's a sentence. The verb is the equality. And so you do manipulations like a string of equalities, an unbroken string of equalities. Let me just quickly look at the chat. Okay, some people said conjugate. Good. Now we have the. So how do, by the way, if I have a squared minus b squared, how does this factor? Someone unmute themselves and say it.
A plus b, a minus b.
Exactly. And this is called the difference of squares factorization. So here, the idea behind the trick of using the conjugates is that we're essentially going to do this difference of squares factorization. I have something which is a square root, and I'm not happy with square roots. I'd like to square them, but I can't multiply by the term itself because a plus b squared does not equal to a squared plus b squared. It's a squared plus 2ab plus b squared. And then I get a cross term. But I can avoid a cross term if instead I multiply by a minus b. So what I get here then is that this is the same as a squared minus h, which is the square of a squared minus h, the square root of that. And then I get minus, again, looking at what the factorization is, a squared. And then at the bottom, I get the square roots of a squared minus h plus a. Sorry, I made a mistake. This expression has pluses everywhere. I don't know why they became minuses. That is an error carried through here, right? I'm just looking at this expression right now, not the second expression. Also, let me plug in my laptop. Now, what is the top of this equal to?
Minus h.
Right, except I just corrected
Sorry,
it.
plus. My
to-
bad.
yes. H divided by the square roots of a squared plus h plus a. Now, look at what we're supposed to show that this is less than. We're supposed to show that this is less than h over 2a, right? And so I won't say anymore. You now need to justify why one is less than the other, right? And that has to do with the fact that the square root function is increasing. So that's already too much of a hint. Okay, so that should hopefully get you most of the way with this problem. And then for problem B, what happens is that the point of the problem is that it's going to show you that this trick of multiplying by the conjugates, there's also a version that works for cubes, not only squares. So in that case, we begin with the expression cube roots of a cubed plus h minus a. And we want to show that this is less than h over 3a squared. And so what you're going to do is the same thing as before. You're going to start with the expression, the cube root of a cubed plus h minus a. And you're going to write this. And remember, I will take points off on your assignment if you write expressions that aren't connected by equalities. It's very important that you have a string of equalities. Mathematical sentences, the equalities are the verbs. A lot of the time, I know that half of you, if I don't insist on this, from my experience of TAing this course many times, will not write equalities. But it's very important to have equalities. It's a very important part of mathematical presentation. It's like writing an English essay using nouns only. You need the verbs in place. The equalities are the verbs. Each sentence asserts a thought. Every single time you write an equality, you in your mind should have a justification for why that equality is true. So why is the first equality true? Because this is multiplication by 1. I've written 1 like this. Why is this true? Because I have, well, I can expand it out, but also I deliberately multiplied by the conjugate in order to get this to happen. Why is this equality true? Well, just reducing the top. Anyway, so you have this expression right here. And so you're also going to multiply it by 1 in a clever way. And then you're going to have something here and something here. And you need to figure out what that something is. But the hints that I've given you is that before the conjugates came out of this expression, right? And now if instead you consider the expression a cubed minus b cubed, that's equal to a minus b times something else, right? And so you need to fill this in, and then that should give you an idea of what the analog of conjugates is for third powers. And then you do an argument similar to here, and then you need to argue that this is less than h over 2a. And I want you to write a sentence justifying why that happens. And then the final part of the problem just uses both of these to rewrite an expression. So you use both of these parts, and then you get something. Any questions about the second problem? So again, why is the second problem being asked of you? One of the reasons is that it has the provocative word show. I'm deliberately putting problems that'll force you to write explanations. And it's not about getting the answer, it's about showing something. And so it provides much more of an opportunity for me to scrutinize your ability to write mathematical arguments. Which is, again, my goal for this class is to get you to write good mathematical arguments. And this will serve you well for any subsequent math classes that you do. And then the other reason is because, well, it introduces several algebra tricks. It introduces the idea of the conjugate. It gives you an idea for why the conjugate works. And it asks you to find a cube analog of the conjugates, coming from the difference of cubes factorization. So just as an algebra exercise, both of these problems have nothing to do with limits and integrals per se, but if you've read my syllabus, I've expressed the idea that calculus is really a problem-solving gauntlet, and a lot of it is just about the algebra. And so knowing rules such as logarithms or knowing how to manipulate polynomials, how to deal with square roots, that's part and parcel of the course. And you've certainly seen that in Calc A as well. Right? Well, so moving on, the problems after this deal with limits and of various sorts. I suppose, okay, I'll also say something about the bonus problem before moving on to calculus material proper. The bonus problem asks you to show, without using calculus, that the absolute value of 3 sine theta plus 4 cos theta is less than or equal to 5. So, sorry, 5. If you were using calculus, you could find where the maximum of this function is using Calc A, but you will get no points for that solution. You are supposed to do this using algebra and using trig identities. So this is a problem in trig identities. And I'll give you a hint. Recall trig addition formulas. And I can give these formulas from memory. I can rederive them. I don't actually remember the formulas, but in my head, there's a technique using complex exponentials for getting these. And so once you know that technique, which I won't be covering here because it's not necessary, you will remember forever. So for example, if you have cosine of alpha plus beta, this is equal to cosine alpha, cosine beta, minus sine alpha, sine beta. And sine of alpha plus beta is equal to cos alpha, sine beta, plus sine alpha, cos beta. And the hints says that there is some alpha such that cosine of alpha is equal to 3/5 and sine of alpha is equal to 4/5. So that's a very big hint. Now, I would actually like you to give me that alpha in terms of inverse trigonometric functions. That would be nice in your solution. But just remember this. And looking at this, well, you can actually use either formula. You can also put 4/5 here and 3/5, and depending on which one of these you choose, you'll use one addition formula or the other, but you only need to use one of them, right? So it's a bonus problem, so I don't want to say any more about it. Although I will take any questions if there are any. Okay, and the reason that I assigned this problem is to remind you about the trig addition formulas. And then I've given you a very big hint that they come in. So this reveals most of the problem. Let's move on to calculus now. Okay, so last time we discussed the notion of a limit of a sequence. So we defined what limits of n of x sub n is equal to L means. And so the intuitive definition is going to be this. Well, first off, what is x sub n? X sub n is a sequence. So for every natural number, we get some real number, x sub n. So for example, if I consider x sub n is equal to 1 over n plus 1, then the sequence is one, 1/2, 1/3, 1/4, 1/5, and so on, right? The natural numbers start with 1, so if I plug in 0 here, I get 1 over 1, that's 1. If I plug in 1 here, I get 1 over 2, that's 1/2. If I plug in 2 here, I get 1/3, then 1/4, then 1/5. And the thing about this is that when n gets very big, these things become small, arbitrarily small, in quotes, in air quotes. And so we'd like to say that x sub n converges to 0, or alternatively, that the limits on n of x sub n is equal to 0. So these are two different notations for the same thing. Any questions about the notion of a sequence? Right, and so what's the intuition for when this is true? That x sub n is eventually very close to 0. And then we also had a formal definition. So what does close mean? Well, let's say that 0 says, give me some space. And so the number 0 asks for some space, and you're supposed to give the number 0 some space. So all possible ways to give 0 some space are given by this thing that we defined before, O0. This is the neighborhoods of 0. And the key property about O0 in general A, let's say, is in OL. In other words, A is a neighborhood of L. And then I'll abbreviate neighborhoods to just neighborhood, NHD, of L. And when does this happen? It happens if there is some interval which I can write as, let's say, A comma B, such that the point L is inside of this interval. That's the space that L has. And this interval is contained in A. So in other words, A is a neighborhood of L precisely when A has some space around it inside of A. L has some space around it inside of A. Does that make sense? It would be helpful for me if people ask questions.
Could you explain that part one more time?
Right. So let's say that this is the number line, right? And let's say that we have a number L here. Then what does it mean to give L some space? Well, what it means is that there is some interval, let's say A and B, around L that's contained in your bigger sets. Let's say this is A. Let's say the red set is A. So we want to explain what it means for L to have some space around it in some set A. And L has some space around it in A if there's an interval that contains L that's contained inside of A. So I'll give you some examples. So for example, the interval 0, 1, the closed interval 0, 1 is not a neighborhood of 0. Why? Because if 0 is in some interval A comma B, then A is less than 0 is less than B, which means that A comma B has negative numbers. So A comma B cannot be a subset of 0, 1, which contains only positive values, right? Does that make sense?
Is there
Yeah.
another way of saying that, just that if it's an endpoint, then it's not a neighborhood?
Yes, so that's one example. There's another example. 0, 1 is not a neighborhood of some number like 17. The number might not even be in the interval, and then it's even worse, right? But on the other hand, 0, 1 is a neighborhood. What's some number that it's a neighborhood of? Can anyone give an example? Well, what's a number that's not an endpoint or not outside of the interval?
0.5.
Okay, someone said 1/2 in chat. Good. So it's not a neighborhood of 1/2. Sorry, it is a neighborhood of 1/2. Why? Because the number 1/2 is inside the interval, let's say open interval from 0 to 1. And that's a subset of 0, 1. Right? Does that make sense to everyone? If not, please ask.
I just have a quick question. So even though, so the line before it where it says that AB has the negative value, so it can't be less than or equal to the 0, 1 interval. Could negative numbers be in a neighborhood if it's a different, I don't know how to ask my question.
Yes. So the fact that negative numbers came into play here is purely accidental and relating to the fact that the interval was 0, 1. So for example, you could rewrite this argument to say that can argue that let's say something like 1, 2 is not a neighborhood of 1, right? And it's the same problem of the fact that it's an endpoint. And then negative numbers have nothing to do with it. But in this case, negative numbers are just numbers that are less than 0, right? So the problem is that it'll contain numbers less than 0, but the interval 0, 1 does not contain numbers less than 0. So I could replace the word negative. I could replace it with has values less than 0, right? Why? Because there are some numbers between a and 0, and those are in the open interval. So that shows that the word negative has nothing to do with it. Does that make sense?
Yes, thank you.
Good. Thanks for asking. Okay, so and then if anyone's still confused, remember that the colloquially idiomatic way is that if you're talking about a neighborhood of L, then the number L says, give me some space. And all possible ways that there are of giving L some space are exactly the neighborhoods of L. Right, so then it comes to the question of what does it mean for a sequence to converge? And the answer is that it means that x sub n is eventually inside any neighborhoods of L. So that's an informal definition because we need to sort of unwrap what eventually is. But I'll give you some examples. Let's consider x sub n is equal to -1 to the power of n, right? So what is x0? Can anyone tell me?
Oh, would that be -1 to the 0?
Sorry, I didn't hear that very well. Can you say that again?
Yeah, that's what I said, what you wrote.
Okay, 1. Good. Yes. Any non-zero number to the 0th power is 1, right? And then if we have x1, that's -1 to the first power. And what's that on voice? Well, it's
-1.
just -1. Good, good. Thanks. And then x2, well, it's going to be -1 squared. And we all know that that's 1. So in other words, this is the sequence. One, -1, 1, -1, 1, -1, and so on, right? So this sequence doesn't look like it's going anywhere. Doesn't go to one place. Right? Because it's oscillating. So if you look at -1 to the n, then we see that this doesn't happen. So for example, I can show that -1 to the n does not converge to 1. How would I show that -1 to the n does not converge to 1? Can anyone, it can be an intuitive answer, or it can be more specific. Anyone want to try?
Just plot it as a graph.
Well, okay. I mean, we can see, I guess it would look like this, right? But why does that tell you that it doesn't converge to 1? We can also go back to the definition. So the intuitive idea is that in order to converge to 1, it eventually has to be in any neighborhood of 1. So the number 1 says give it some space. Let's give 1 some space. What's an example of a neighborhood of 1? Let's consider, so I am going to tell you the answer. Let's consider 1/2, 3/2, right? This is a neighborhood of 1, isn't it? 1 has some wiggle room around here. 1 is inside of here and it has an open interval around it, manifestly, because the entire thing is just an open interval. The word open interval just means an interval without the endpoints, right? So does anyone have any questions about why this is a neighborhood of 1? You've given 1 some space, right? Good. Okay. Well, now, if we look at n odd, when n is odd, what does x sub n equal?
-1.
Good. and notice that -1 is not in this neighborhood. So so x sub n is not eventually in the neighborhood 1/2, 3/2. And someone suggested graphing it. Well, we can actually see what this means on the graph. So if I look at the neighborhoods 1/2 to 3/2, that neighborhood looks like this, right? That's that neighborhood. And we can see whenever the number n is even, whenever the index n is even, it's going to be in that neighborhood. But whenever the index is odd, it's not going to be in that neighborhood. And in order to eventually be in that neighborhood, it has to happen that after some point, everything else is in the neighborhoods. But that doesn't happen here, right? So we've looked at this sequence, -1 to the n. And I've given you a careful argument about why it does not converge to 1. Well, you can also say that it doesn't converge to any other number. It's going to 2 specific different places. So for every single other number, I can also find some neighborhoods so that it's not inside both of them. And this is not a careful argument, but you can intuitively understand why that happens, right? It looks like the sequence isn't going to any one place. And this notion is a way to capture what it means to eventually go to one place. So going back to the homework, problem 3 on the homework asks you to consider for R a real number, the sequence x sub n is equal to R to the n, right? And we've considered this sequence for R is equal to -1. So we saw that when R is -1, what happens is that the sequence bounces between 2 values and it doesn't go any specific place. Well, then you're supposed to figure out how does the sequence behave for different R. And when does it converge? So that's the problem. I changed the statement before from being something that asks you to prove something. Well, it asks you to show something. I won't use the word prove in this course. It's not proof. You're not doing proofs. The word proof is scary, so I'm not going to use it. It asks you to show specific results and that you'd have to do a more careful argument. But right now it's more of a writing prompt. You can consider what I said and that analyze the case -1. If you actually try a bunch of values, you notice that the behavior falls into several different patterns. And I'd like you to make a statement that covers all of the cases. And so I want you to do this analysis, and that would be nice. So you need to tell me exactly when does it converge and to what value it converges if it converges. And then to what value converges, it's how does it behave for different R, right? So I want you to tell me the behavior for every R. And then you just do this by playing around with the sequence and seeing what values you get. And then after you've done all of these experiments and figured out a pattern, you write the pattern up and I'll see if I'm happy with what you've written. Sounds good? So that covers another problem on the homework. Now, technically, I can be more formal, although that's not required. So if we want to be formal, eventually means that there is some n, capital N, so that x sub n is in A. That's our neighborhood of choice. When little n is bigger than or equal to capital N. And so this is written up in the notes. So the formal definition, I suppose, is I guess I can rewrite the statement formal. X sub n converges to L if for every neighborhood of L, there is some number so that it's eventually in that neighborhood. You don't have to memorize this formal definition, and I won't be asking you to do too many arguments using the formal definition. That's just for your personal enrichment if you feel like it. But you should understand the intuitive definition about the sequence going somewhere. And then you're asked to do this analysis for what happens with the sequence in general. And it's a good exercise. It gets you playing around with things and it gets you thinking about things. Any questions about this problem? Okay, I've been going on for an hour, so we're going to take a break in a bit, but I'd like to discuss some other things. From calculus A, oh, let me do the exercise. Sorry, let me actually give a formal argument. So I will give you an example of a formal argument. And this is going to be, so the claim is that for the sequence x sub n is equal to 1 over n plus 1, limits on n of x sub n is equal to 0. And this result, you're actually going to use very frequently. So in the homework, you're going to need to know that the limit of 1 over n as n goes to infinity is 0. It's used a lot of times. Now, here's the solution. So instead of perhaps writing claim, I'll write problem, example. Show that. And then I'll change this to a lowercase f. So how would I do this? Well, I need to show that for every neighborhood of 0, the sequence is eventually inside that neighborhood of 0. So I begin by taking some neighborhood of 0. Let's A be a neighborhood of 0. Then I write what this means. This means that there are, well, let's say there is some interval with 0, a point of this interval, contained inside of A. So this is just what it means to be for A to be a neighborhood of A. Now, 0 is in this interval, means that A is less than 0 is less than B, right? Everyone following so far? Right. So now I consider the number 1 over b. This is a positive number. Because b is strictly greater than 0. So 1 over b is going to be some positive number. Now I'm going to say, let's capital N be the least natural number greater than or equal to 1 over b. Or AKA, that is, I can say that is, n is equal to the ceiling function of 1 over b. So 1 over b might not be a whole number, and I'm just going to take the smallest whole number that's greater than or equal to 1 over b. What this means is that I have 1 over b is less than or equal to n. So that's good. Now what? Well, then if little n is greater than or equal to capital N, I have x sub n, which is 1 over little n plus 1. Well, that's less than. So if I divide by a bigger number, I get something smaller than if I divided by a smaller number. So 1 over n plus 1 is less than 1 over n. Let's say for n is greater than 0. Well, actually, n is definitely going to be greater than 0 because capital N can't be 0. And then, well, if I look at this little, again, dividing by a smaller number gives me something bigger. So I can rewrite that as less than or equal to 1 over capital N. And then dividing by a smaller number gives me something bigger. So I can replace that with 1 over b. Sorry. And that's equal to b. So in other words, x sub n is less than b. And a is less than 0, is less than 1 over n plus 1, which is equal to x sub n. So a is less than x sub n is less than b. So x sub n is in the interval a, b, which was inside of my a. In other words, I've shown that eventually, whenever little n is bigger than capital N, I have that x sub n is in the space that I had around 0 by virtue of a being a neighborhood of a. And so that completes the argument. So this is how you can carefully show. I've been very, very precise and very careful. And notice that when I wrote up this argument, a lot of the argument consisted of English sentences. So I think the way that I've written this up, it's a fairly good example of a mathematical write-up. So if you think of mathematics as being an analytical English essay, This is an argument that you can read and you can follow the arguments. Every single sentence expresses a thought and one thought follows after the other. The first thought is I need to show that for every neighborhood something holds. So I let A be some neighborhood. Now, what does that mean? A is a neighborhood of 0 means that there's some interval. So that 0 is an AB is a subset of A. Now, what does that mean? Well, that means that I have this bound. Now I go on to the next thought, consider 1 over B, right? Now this is a positive number, so let n be the least natural number. N was required to be a natural number in the definition. And then I go through it. So you're not going to have to write arguments like this, but this is a very, very careful argument for why the limits of 1 over n goes to 0. Now, if I'm not careful about indexing, then I can also just write that the limits on n of 1 over n is equal to 0. Finally, before we take the break, I am going to tell you how you actually work with limits. From calculus A, recall limit laws. And if we recall what those limit laws are, we have, for example, if x sub n goes to L and y sub n goes to L prime, then, or let's say M, then x sub n plus y sub n goes to L plus n. So in other words, limits distribute over addition. Similarly, x sub n times y sub n goes to L times n, right? And if m does not equal to 0, then x sub n divided by y sub n goes to L divided by m. Otherwise, we get is divided by 0 error. So there are a bunch of things like this, and they can let you prove properties. So I can give you an example. The limits on n of 1 plus 1 over n. How do I evaluate this? Can anyone tell me? How would I write up an argument to show what this limit is? Using limit laws. So I have a sum here. What can I do with a limit of a sum? Okay, people aren't following, which means that people got lost somewhere. Can anyone ask questions to clarify what they don't understand? That would be very helpful for me. So for now, forget about the thing that I presented above. Just think about the fact that there are some limit laws like these. Is anything not clear about these limit laws? Let's get some participation.
So would the example be the limit of n of 1 plus the limit of n of 1 over n?
Yeah, good. So the limits on n of 1 plus the limits on n of 1 over n. I guess I can write it like this. And now, well, we can think of the number 1 as being a constant sequence. It's the sequence 1, 1, 1, 1, 1, 1, 1, right? What does that converge to?
1.
Exactly. And then we've already done this example right here. I've given you a very careful formal argument that the limit of 1 over n is 0, right? So that's just 1. So in other words, if you know one example, if you know that the limit of 1 over n goes to 0, then you also know, for example, the fact that the limit of 1 plus 1 over n goes to 0. Let's do a more interesting example. Let's say you have something like 1 plus 1 over n times 2 minus 1 over n divided by 3. Then how can I rewrite this? Someone else? More participation. Oh, by the way, let me just say one more thing. If k is a number, then limits xk times x sub n is equal to k times the limits of x sub n. So in other words, I will not distribute the limit to the bottom. I'll just pull the 1/3 out of the limit. That's also allowed. Okay, so what do I have here? Well, I could do several things. I could multiply this out, but what if I don't want to multiply this out? What can I do with the product and the limit? Anyone? Okay, there's a comment in the chat. Distribute by the quotient rule and the product rule. So yes, I can do that. And I'm not going to use the quotient rule. I'm just going to pull the 1/3 out of the limit using this rule. But for the top, I'm going to distribute this by a product. So I can say that this is 1/3 times the limits of 1 plus 1 over n times the limits of 2 minus 1 over n, right? And then if I'm going to be a bit sloppy, I'm not going to write the limits on 1. I'm just going to take it out. I'm just going to do 2 steps in 1 and say that this is 1 plus the limits of 1 over n and 2 minus the limits. Just to also be clear, these are grouped together. And then this, we know what those limits are. And so that's just 2/3, right? So you have limit laws, and limit laws are great. And then the last limit law that I have to remind you of is if f is continuous, which we'll discuss what that means in a second, then the limits on n of f of x sub n is equal to f of the limits on n of x sub n. So limits commute with, they go inside of continuous functions. So for example, the function square root x, what's the domain of this function, by the way? Where is this function defined? For which x?
0 to infinity.
Exactly. And I can say has domain x is greater than or equal to 0. You can't take square roots of negative numbers. So that's a thing that we have to remember. Good job. Okay. Now, right. Whoops. Here we are. So for example, if I look at limits on n of, let's say, 1 over the square root of n, which is the same as the square root of 1 over n. Remember that if I remember just this is an aside about exponential rules. Square root of a is equal to a to the power of 1/2. And if I have a over b to the nth power, that's a to the nth power divided by b to the nth power, right? So look at this. If I consider this as a square, the square root as a continuous function, what can I do with the limit?
Would you put it to the 1/2?
Well, I can just, I don't have to rewrite it to the 1/2. This is just a reminder. So the reason that I wrote this here was to remind you of this equality, right? We can also, the square root of 1 is also the square, 1 is also the square root of 1, right?
Oh, yeah.
So that just reminded you why this is true. But now the square root of x is a continuous function. Let's just suppose that it's a continuous function. So what does this rule? What does the rule let me do?
Can you make it so that it's a square root of the limit of n?
Exactly.
Yeah.
And now this one example we've computed. So we did exactly one limit formally. We very carefully justified why the limit of 1 over n is equal to 0. And we see that limit laws from that let us get a bunch of other limits. So that's the square root of 0, which is 0, right? So that evaluates that limit. So finally, I'm just basically giving you all the homework solutions this class. Question 4 asks you to consider the limits on n of the nth root of 2 to the n plus 5 to the n, right? And I'm going to let you assume, you are allowed to assume that f of x is equal to the nth root of x is continuous. And by the way, in your write-up, if you want to write a good write-up and you want to write a good argument, then you should actually write this as an English sentence. You should say, because this function is continuous, I am allowed to bring a limit inside of the function, right? So write good answers and justify everything. But you are allowed to take this as given. And so that comes into this problem. You need to do an algebraic manipulation, and then eventually you'll get the limit of something. Now, you won't get the limit of 1 over n. You won't get 1 over n. Instead, you'll get something to a power, right? But what was problem number 3? Problem number 3 asks you to consider what happens when you have powers. So for example, if you have 2/5 to the power of n, will come into play. And this is where you use question 3, right? So in question 3, I'm going to ask you to consider another limit, which is the limit of these nth powers of terms. And that's another limit, and you're going to have to do it, you can do it in a hand-waving way. So you don't have to formally justify it in the same way that I formally justified this. You can try if you want. I'd be happy if you did. Although it's not necessary. But if you have a correct result, if you figure out what it is, then you should see how manipulations come into here. And so why is question 4 assigned? Question 4 is a good problem in using the limit laws. And I'd like you to actually write up your answer like I'm writing it up here, where I actually play with the limits. I write that the limit of this is equal to the limit of this. Remember, math is an analytical English essay, like an analytical English essay. The equality signs are verbs. Every time you say something is equal to something, you're making a statement. And in your head, you have to know why it's true that you can make that statement. So this is this. Why? Why? Because of the limit law of distributivity. Why is this equal to this? Because of the limit law of distributivity over addition. This was multiplication, this is addition. And then I've also done 2 steps in one. I've also know that the limit of a constant sequence is just its value. And so you can see that then if I write the string of equalities, it is a sequence of faults, one following after the other. And it's an essay in the language of mathematics. It's a paragraph in the language of mathematics. It's expressing an argument for why the top quantity is equal to 2/3. And you have to write these equal signs. If you don't write equal signs, I will take off points and I will be pretty disappointed, right? So one thought after the other, clean, nice presentation. So I'm going through these examples to show you. And also I'm basically giving you the solutions to the homework. So we're going to take a break now, although I'll take any questions before then. Okay, so there are 8 problems on the homework. We've already discussed 5 of the problems, and then we're going to need to discuss the next 3 problems later. I mean, after the break. But we're also crucially going to come up to a very important topic in this lecture, and that's the definition of an integral, which is the goal of the first week of this course. Okay, sounds good. So let's say it's 26, 30, 40. Yeah, let's give everyone a 15-minute break. So we'll resume at 7:40. Okay. And then if you think of any questions during the break, I can start off with questions at the beginning of the session after the break. Okay, I'm going to get some coffee. I recommend you do as well. See you. Okay, it's time, good. So welcome back, everyone. Oh, turn this on. Okay, are there any questions that people have thought of during the break? So in the remainder of the lecture, the most important thing is going to be integrals, but before then, we're going to go through one intermediate topic, which is limits of functions. Okay. Now, what does this mean? In calculus A, we saw a lot of the limits as x tends to a, as x approaches a of f of x. So we had this expression here. Now, what does this mean? Well, before what we had was a sequence. Here we don't have a sequence. Here we have a point that's approaching A. And what does this definition intuitively mean? Intuitively, limits as x approaches A, sometimes it's good to write this under, of f of x equals L, means that's when x is sufficiently close to A, f of x is arbitrarily close to L. And of course, then we have to unwrap what these loaded terms mean, sufficiently close and arbitrarily close here. Well, first off, we know one thing. We know that closeness is parameterized by neighborhoods, right? So close should correspond to neighborhoods. So I abbreviate neighborhoods to just NHD. And then what did we have before from last time? If we consider O of A, this is a directed set. What does that mean? That means that neighborhoods can get smaller, right? And in general, for any two neighborhoods, you take their intersection, that's a smaller neighborhood of A. So we can imagine an order where higher up we have smaller and smaller neighborhoods, and it eventually closes in onto just the point A itself, although that's not a neighborhood of A. So we can imagine just squishing a neighborhood, right? And in the same way that we took a limit along a sequence, you can think of taking a limit along neighborhoods as the neighborhoods converge to just a point, although there is, for example, the limits as of n goes to infinity of x sub n, infinity doesn't exist. There's no number infinity. There's no such term x infinity. And similarly, if we look at neighborhoods of the point A, the neighborhood that's just the point A, that's not a neighborhood, so that doesn't exist. But we can imagine the neighborhoods converging to just the point A, in the same way that you might write the limit as n goes to infinity of x sub n. Although I haven't been writing it like this. I've been writing it as just limits subscript n of x sub n. But anyway, that's an aside. So what does it mean arbitrarily close? Well, if B is a neighborhood of A, I can consider a set, and I'll write this set as F square brackets B, and this will be the set of all values f of x such that x is in B. And this is called the image of B under F. And so these are all these are all of the values that F takes on the set B around this neighborhood. Being close, let's see, there's a question in the chat. There is never an instance where n is equal to infinity. In order to define a sequence, you do not specify what n is at infinity. So it's not part of the definition of a sequence. So in other words, you can't assume it. I mean, you might define n infinity, but that's not part of a sequence. The definition of a sequence doesn't include n infinity. It just includes n subnatural numbers. Now, similarly, we just have the value, for example, a and the value f of a, but we're not considering that because that's not a neighborhood. We want to say when it's sufficiently close. Right? So then f of x, so here are all of the values that f takes in a neighborhood of a. And what does it mean arbitrarily close to L? Well, arbitrarily close is parameterized by some neighborhood. So closeness closeness to L is given by some neighborhood A of L. And thus, we can consider the condition that f of B, all of the values that f takes on the neighborhood of B, all of those are close to A, as close to L, as parameterized by the neighborhood of A of L. Sorry, I'm not being very clear. So I'll give you the formal definition, although again, so the formal definition, and remember, the informal definition is that when x is close to A, f of x is arbitrarily close to L. Well, how do we write that up formally? Limits as x goes to A of f of x is equal to L if for every neighborhood A of L, there is some neighborhood B of A, so that's the image of B under F is contained in A. So in other words, when X is sufficiently close, remember, closeness can't be precise. Closeness has to have some wiggle room. So we give some wiggle room around A, so that whenever we look at the values within that wiggle room, they're within the specified precision corresponding to A. So this is the formal definition. It's a bit shorter than the formal definition that we had before for convergence of a sequence. And it just intuitively captures these two things. So sufficiently close to A is parameterized by some neighborhood of A, and sufficiently close to L is parameterized by some neighborhood of L. Now, to be within that closeness means that all of the values that F takes on B, they're inside of A, right? So we can unwrap it like this, and this definition doesn't actually look too bad, does it? If you understand the notion of a neighborhood, then it's just for every single precision around L, we can find some precision marker around A, so that all of the values in that neighborhood of A live inside that neighborhood of L. And I guess we can draw some graphs to give an example. So let's consider the function f of x equals x squared. And then let's consider something like the value 1 and then the point 1 here, right?
May I just ask a quick question
Of
about
course.
the purple box? For the second line where it says there's some, it's the E is the interval symbol and then the O is the neighborhood symbol, right?
Yes.
Okay, thank you.
So that should be a B. And then yes, sometimes my neighborhoods look like thetas. It should be open like this.
Okay, thank you. And then so after the B, it's the interval symbol, right?
So I have a special notation right here, a different notation for what it means to consider all possible values of a function on some sets. So this is not the interval symbol. This is the symbol for the image of B under F.
Okay,
And so, for example, if B is the interval 0, 1, then so I'll give you an example. Suppose that f of x is equal to x squared. And then let's say that b is equal to the interval from 0 to 2, right? Then I have, for example, f of 0 is equal to 0, f of 2 is equal to 4, and then all of the values in between. So I'm going to put together all of the possible values that f can take anywhere on this interval. And we find that if we look at the image of f on the interval 0 to 2, what is that equal to? Okay, this is actually going to be a bit confusing. Technically, I should put 2. I don't want to double load this. F of B. I would have to write 2 brackets. Okay, what is the image of f on the interval 0 to 2? So in other words, as x ranges from 0 to 2, what does f of x equals x squared range from? Anyone?
Could you repeat the question one more time?
Right. So I'm considering the interval 0 to 2, closed interval 0 to 2, and I'm considering the function f of x equals x squared. Now I have this notion of the image of B under F, right? So I would like to know what the image of this interval is under this function.
would it be 0 to 4?
Exactly. And so that's the notion of an image. It's all values that f takes on the interval B. Great. Right. So then let's look at this. X squared at 1 is 1. Now I'm going to claim that the limits as let's say x goes to 1 of x squared is equal to 1. And now what would that mean? That would mean that for every single neighborhood of 1, so let's say I give this neighborhood right here, right? And let's say I drop this dashed line here to here. So I would like to, for that neighborhood, I'd like to find some neighborhood of around this point here, so that the values that f takes on range within here. And if I look at this, if I sort of drop this here and here, then if I take this interval here, that interval maps within this interval, right? Let me draw this picture a bit bigger. So let's say I take an interval here. This is some neighborhood of this point. Then there exists some neighborhood around this point, which I can maybe look at like this. And when I look at the values inside of that neighborhood, it gives me this, which is inside the green neighborhood, right? So that was what it would mean for this to occur. Now, I actually do this example carefully. I will show you example. Let's f of x is equal to x squared. Then the limits as x goes to 0 of f of x is equal to 0. And I do this in detail. Does anyone have a question about the general intuition behind this definition? Sorry, oh, you weren't clear about the notion of a neighborhood. Okay, good question. Yes, let's definitely worth reviewing. And yeah, so more than one person. So I should be honest, I think that I have a bit of lingering regrets about the fact that I decided to do neighborhoods for all of these definitions. It's possible to avoid using the notion of a neighborhood, but you'd have to rewrite everything, and I've chosen to write it in a certain way. Now, what's the idea behind a neighborhood? Wait, I introduced neighborhoods here. So let's say, let's consider the notion of a neighborhood of 0. A neighborhood of 0 is going to be some set of real numbers so that the number 0 has some space around it in the neighborhood. Now, what does it mean to have some space around it in the neighborhood? It means that there's some interval. So I'm here defining what it means to, for a set A to be a neighborhood of OL. So first off, what is A? A is a set of real numbers. Now, what would it mean for that set to be a neighborhood of 0? It means that 0 is inside of A, and that further, that L is inside of A, and that L has some wiggle room around it. Now, what does it mean to have some wiggle room? It means that I can find some interval so that L is inside that interval and that interval is contained in A. Now, what does an open interval on the number line look like? So on the number line, every single open interval I can write like this. So it doesn't include the endpoints, and it's all points between two values, not including the endpoints, right? So if L is some point in here and we have an interval around L, then that looks like L has some space around it, right? L can't be the endpoint. L can't be either A or B because L has to be inside of this interval and this interval doesn't include the endpoints. So if L is inside some interval, then L has some space around it, right? And I'm requiring L to be in the interval and that interval to be a subset of A. So A, in other words, is a neighborhood of L, is n sets. It can be pretty complicated, right? So long as it includes some wiggle room around L. And then I give an example. If we look at an endpoint of a closed interval, then that's not a neighborhood of that point. Why? because there's no wiggle room around 0 here. Because if I look at any interval around 0, it has to extend past the endpoint. Does that make sense? So for the people that ask the question, I really want your feedback on this as well. Could I get some feedback from the people who asked the question? Is it clear? Okay. So what's the only important thing that when it comes to neighborhoods? The important thing is that whenever you start off any arguments by saying that something is a neighborhood, you immediately say what this means. You immediately say that there's some interval around the point in A. So really, when it comes to neighborhoods, you sort of immediately unwrap the statement like this. And then instead of, you can replace the word neighborhood of A with open interval around A, right? Because we essentially pass to an open interval of A whenever we take a neighborhood. You just write this sentence down every single time you're doing an argument with it. Okay, let's go back to here. I need to get to integration today, so I need to go through this a bit quicker. There's only one homework problem about this, and then integration has 2 homework problems, and integration is much more important to this course. Okay, so what's the solution? I want to show that for every parameterization of wiggle room around 0, in this case, we're not looking around the point 1, we're looking around the point 0. So if this is my parabola, then I want to show that for every amount of wiggle room that I give around 0, there's some parameterization of wiggle room that I can give around the 0 on the x-axis, so that the values that f takes on in this interval lie inside the green range. Now notice that all of the values that x squares takes are non-negative, right? Because the square of any number is greater than or equal to 0. Anyway, so what's the solution? Let's A be a neighborhood of 0. This means, so unwrapping the definition, that there is some interval A comma B with 0 is in, because it's a neighborhood of 0, A comma B is a subset of A, right? So what's the key point about neighborhoods? The key point is that a neighborhood contains an interval around the point of which it's a neighborhood. So because we're dealing with neighborhoods, we immediately unwrap the statement and then we just have an interval around 0, right? Okay, what do we do next? Now we'd like to show that we'd like to find some other interval around 0 so that f of x is within the values a, b. Let me just look at my notes for how I wrote this up. I know how to do it, but I want to write it in the cleanest way possible. Okay, then I write the next thing. Since 0 is in the interval a comma b, this means we have a is less than 0 is less than b, right? So b is a strictly positive number. Now, since b is greater than 0, it makes sense to take square roots of non-negative numbers. The square root of b makes sense. That is, b is not less than 0. Now, I'm basically going to consider the interval. Now let B equal negative square root of B to square root of B, right? B is greater than 0. Since B is greater than 0, this is a neighborhood of 0. Now, if X is in B, then negative square root of B is less than X is less than square root of B. And so to see how multiplication works, X squared is less than or equal to the square root of B squared. Sorry, less than, strictly less than. And that's equal to B. So we have, so f of X for my function X squared is less than B whenever X is in this interval. Does that make sense? Okay, now also f of X is greater than or equal to 0 because it's the square of some number. And A is less than 0. So we have the reverse direction. We have A is less than f of X is less than B. So f of X is in A comma B, which is a subset of A. And this is true for every single X. So f of for every X and B. So f of B lives inside of A. And that completes the arguments. Now on the homework, okay, are there any questions about this argument?
I have a question. I apologize. I have a lot of questions tonight.
No, that's good. I'm happy. More questions is good.
Where it says x squared, no, sorry, I'm looking at the wrong area. It's the fourth line down from the solution.
Okay.
The last parenthesis after makes sense. What does that say? I can't read it.
Oh, sorry, this is IE. That is, right? IE is the abbreviation id est for that is.
Okay, and then it's
B is not less than 0.
okay. Thank
So
you.
in other words, if B were less than 0, then B would be a negative number. And it does not make sense to take the square root of a negative number, right?
Right. Okay. Thank you.
So here I'm justifying the fact that I am allowed to take the square root. Okay, any more questions? So what's the important thing? Look at this picture right here. We start with some precision. Let's say this precision contains an interval from A to B, right? Well, then what I'm doing then is I'm saying that if I consider the interval here from negative square root of B to square root of B, right? Whenever I square those values, they're going to lie in the interval AB. Right? And my goal is to find some interval around here, some neighborhood of 0, so that when I look at the image of x squared on that neighborhood, it lives inside of this other, the neighborhood A, capital A of 0. And capital A contains this interval. So that's how it works by construction. So on the homework, this is problem 5 for the homework. You are asked to show that the limits as x goes to a of x squared is equal to a squared for all values a. So here I've done the example for 0. What you're supposed to do is you're supposed to take this argument, and it's written up carefully in the notes, and you're supposed to extend the argument so that it works not just for the number 0, but it works for all possible numbers. And by the way, so if f of x is equal to x squared, then this says limits as x goes to a of f of x is equal to f of a. And this means this is the meaning of f is continuous at a. So the meaning of continuous is precisely that the limit as x goes to a of f of x is equal to f of a, right? So I'm this problem 5 asks you to show that the function f of x equals x squared is continuous, and you're not allowed to do it using limit laws. You're supposed to do it in a careful way, emulating this argument. So how do you solve this problem? You go through this argument, it's written up in the notes, and you modify it so that it works for all possible a. So remember that I expect each one of these homework problems to take you more than an hour. Although now it's, I've given you a lot of hints, but this problem will still, I'm not giving away too much more. This problem will take you longer than an hour. So you have to be really careful, and you have to get something to fit inside of the other thing. And you have to do some algebra in order to get that fitting to occur. So that's a bit of a challenge. I think this is one of the harder problems on this assignment. Sounds good? Okay, I need to move on to integration because this is the main thing about this lecture. So how much time do I have left? Okay, I have an hour to cover integration, a bit more than an hour. So what's the problem that we are dealing with? The problem is what I showed you last class at the beginning of the second half of the lecture. Suppose that we have some function and we have some interval a, b, right? We're going to take this region bound by the function, and we're going to shade it in. And then the question that we're going to ask is, what is the area of the shaded region? And we're going to define this formally. And if you remember how I started last lecture, it was about the Greek definition of area, or the Greek notion of area more precisely, because they didn't technically define areas, they defined ratios of areas, but that was sufficient. And we're going to see that there are a lot of those ideas exactly come through in here. Mean to talk about area. And there was one more clarification for this notion. What happens if the area, if the graph dips below the x-axis? And what happens is this area counts for negative. So area, in other words, it's more accurately assigned area. Okay, so our goal is to define when this makes sense, right? Is that clear? Any questions about the notion of signed areas? Okay, so before then, I want to talk about the notion of maximum and minimum values, or it's actually going to be called inf and sup. Well, soup. So what these are is that suppose A is some set of real numbers, right? Then A is bounded above if there is some M real number, so that X is less than or equal to M for all X in A. So in other words, it's an upper bound. If there exists an upper bound for the sets. So for example, if we look at the number line, always go back to the number line. Let's suppose that the set A looks like this, right? Suppose this is the set A. Well, then M here is an upper bound for A, right? It's bigger, it's greater than or equal to all of the values in A. So I can give you an example. 2 is an upper bound. For the interval 0 to 1. Right? Does that make sense? Any questions? Okay, well, notice that 1 is also an upper bound of 0, 1. Because I have the sign greater than or equal to here, or less than or equal to here. So an upper bound can be a point of the set if it's the biggest point. And in some sense, one is the best upper bound that you can give. Or I can also call it the tightest. I can give, right? Because if I go any lower, then it's no longer an upper bound, right? So the best lower bound is called the best upper bound of A is called supremum of A. This is often the maximum. But it doesn't have to be. So for example, if I look at the supremum of the open interval 0 to 1, what's the best upper bound that I can give for the open interval 0, 1?
1.
Yeah, and 1 isn't actually a point in that interval. So the best upper bound doesn't have to be in the interval. But if I had the endpoint, then it would be the maximum value. The maximum value doesn't always exist because there is no maximum value in the open interval 0 to 1, right? But there is a supremum. And so the real numbers are very special. R is very special. If A is non-empty and A is bounded above, then sup A exists. And in the notes, I discuss, for example, how this is not true of rational numbers. So for example, you can have that the supremum of some set of rational numbers is an irrational number, but that's not a rational number. So in some sense, the rational numbers wholes, and this property isn't satisfied if you just look at rational numbers, and you're only allowed to give rational numbers as bounds. So I'm not going to go into detail with that here because I want to keep the technicalities as low as possible. But this is basically a generalization of the maximum value. Sometimes the maximum value doesn't exist, and then the notion of a supremum fixes that. Any questions about that? So really, the key to understanding it is just understanding this example. This example does not have a maximum value, has no max, but it has a sup. So sup is a better version of max. And I guess this line right here is the informal definition, right? So this is what you need to keep in mind about this. I'm going to keep the technicalities as low as possible. And similarly, we can talk about lower bounds. Lower bounds. And the best lower bound, in other words, the biggest lower bound of A is called inf A. And so these are called the supremum and the infimum. And those are just some technical terms. And then inf is the, this is a better version of min. Okay, so that this is all that's important. A non-empty sets that are bounded below have an inf, and non-empty sets that are bounded above have a sup. And then if A is bounded from both, if A is bounded both above and below, we say that A is bounded. Right. Now, also, suppose we can also extend this definition to functions. Suppose f is a function, and f is defined on some interval a, b. Then we say, let's call this interval b. Then f is bounded on b if the image set is bounded. So what are some examples? Just what does the word bounded mean? Well, it's pretty intuitive, right? For example, let's suppose that b is equal to -1 to 1. And then let's consider the function x squared, right? And then let's consider the function 1 over x. So the function x squared is bounded on -1 to 1, while the function 1 over x is not bounded on the interval. Not bounded. So that's pretty straightforward, right? This isn't bounded, it escapes to infinity. This is bounded. It's contained, it has an upper bound, its values don't exceed 1 on this interval, and they don't go below 0 on this interval, right? Any questions? Right, okay, so let's get to the definition of area then. Suppose I have this example from before. This is my function right here. And this is my interval a to b. So what I'm going to do is I'm going to consider slicing up this interval into several pieces. And then what I'm going to do is that I'm going to look at each piece and I'm going to look at the function's values on that piece. And then I'm going to find the maximum value that it takes, or in other words, the supremum of the values. So let's draw this with a line. So on this interval, this looks like the supremum, right? And then I'm going to consider forming a rectangle with heights the biggest value that it gets on here, right? And then I can also consider alternatively taking the lowest value that f takes on here. And I can form all of these rectangles. Now, if I look at these lower rectangles, that's the sum of their areas is a lower bound for the area under the curve, right? So this right here, what we're trying to find, this is called the area under the curve. And if I take any subdivision of this interval and I take the lower bounds of f on each interval and I form these rectangles, then the sum of the areas of these rectangles is a lower bound on the area under the curve. Does that make sense to everyone?
Can you repeat that, please?
Right. The area under the curve, it looks like this, right? This is the area under the curve. Now, what about these rectangles? These rectangles look like this, right? These are the lower bounds. And the area of the blue is less than or equal to the area of the green, right? So what I said is that the sum of the areas of the blue rectangles, it's a lower bound for the area of the area under the curve. Does that make sense?
Yeah.
Okay, and conversely, we can consider the bigger rectangles. And then these areas, that's an upper bound for the area under the curve, right? So the lower rectangles, the sum of the areas of the lower rectangles. So is suppose K is the area under the curve. Let me check how I am for time. Okay, then let's say this A is equal to the blue area. And that B is equal to the red area. Then what we have is that A is less than or equal to K, which is less than or equal to B, right? So remember what the Greeks considered. For the Greeks, they considered the circle. And they considered inscribing polygons inside of the circle. And then they subdivided this polygon. And these iterated subdivisions, they were essentially approximations to the area inside of the circle. Well, this would be an approximation from the inside, and similarly, you could take an approximation from the outside. These sides are supposed to be tangent, if I could draw a bit better. And then you could take an approximation from the outside. So we're doing a similar thing here. We're taking an approximation from the outside, an upper bound for the area, and we're taking an approximation from the inside. Now, for the Greeks, what was important was that eventually the inner approximations exhausted the leftover area. So eventually there was no area left over. If we were to draw the leftover area, then this area right here, that's the leftover area between the area under the curve and the lower approximation, right? Does that make sense? So what we'd like is when the subdivision gets arbitrarily small, when it's arbitrarily fine, we would like this leftover area to go to 0 from both sides. And then if the upper bounds and the lower bounds close in on a single value, then we say that the function is integrable. And we say that the value on which these upper and lower approximations close in on is the value of the integral of the function on that interval, or the area under the curve. So we're going to call the area under the curve. I'm going to write this right here. This area under the curve, we will call this so suppose this function is f. We will call this the integral from a to b of f of x dx. So this is a piece of notation. We're going to explain why this piece of notation is used later. But if the area makes sense, then that's the expression, these are the mathematical symbols that we will use to refer to the area under the curve. Capiche? Okay, so how do I actually define what these lower and upper approximations are formally? So I'm going to go through that. So first off, we need to talk about partitions. How much time do I have? Okay, I need to be very careful. So a partition I'm going to fix a convention. Let's I be a closed interval from A to B with A is less than B. So it's very important that we understand whenever I refer to, sorry, I'm not going to call this I, I'm going to call this L. I is a bad letter to choose. So L is going to be an interval, a closed interval AB with A is strictly less than B. So it's going to be a closed interval that's not just a point. It has actually properly fills. So a partition of L is equal to A comma B is, well, it's a set of these endpoint markers. It's a finite subset of L that contains A and B. So we will write, we will write the partition P as P is, we'll order the points. So we're going to write that A is X naught, and that's less than X1, and then that's less than Xn, which is equal to B. So what is a partition, in other words? Let's suppose we go on the number line, and on the number line, we have the interval from A to B. So a partition is just any collection of points, a finite collection of points that includes A and that includes B. So here in this diagram, we decided to divide the interval into these pieces. We could specify what these pieces are by specifying all of these endpoints, right? So a partition is just a specification of the endpoints, and it has to include the endpoints of the interval. Does that make sense?
Can you repeat that one more time, please?
Sure. So here, when I subdivided this interval into pieces, I could specify what these pieces were just by saying what the endpoints of these pieces were, right? So if I tell you what values these points have, then I've also specified how to divide it into these pieces. Does that make sense? So I haven't finished the explanation, but does it make sense how this subdivision is defined by its endpoints?
Yes.
Right. So what is a partition then? A partition of an interval AB, it's going to be a finite collection of endpoints. So we're only allowed to divide it into finitely many pieces. And we want the endpoints of the interval to be included as boundary points in the subdivision. And then when we actually write what a partition is, we'll order the endpoints and we'll call the points in the partition x0 to xn. And then we'll write A is equal to x naught is less than x1 is less than ... is less than xn is equal to B. And so what is the meaning of a partition? Well, the meaning of a partition is, let's say our interval L is AB on the number line, then this would be x naught, this would be x1, and this would be xn, right? So a partition is just a specification of the endpoints containing A and B. Does that make sense? Okay, and so what we'll do is we will write delta L for the set of partitions of L. So in other words, P is in delta L means that P is a partition of L. Okay, I am now going to take what I had in the notes and I'm going to simplify it. I'm going to give you a much simpler definition. So in the notes, the definition technically, to me, it's more logically precise, it's more logically appealing. It connects the definition of integrals to the definitions we had before. But I'm going to give you a shorter version of that, which leads to more directly into computations. I suppose before I give you that definition, I need to tell you one more definition. So here we had the area of the lower rectangles and the area of the upper rectangles, right? I'm able to actually define. So if F is defined on L is equal to A comma B, then I define, then consider the lower sum. Before I say then consider, then consider for P is equivalent to A is equal to X naught is less than Xn. So for then for P is in delta L. So for some partition of L, consider the lower sum of F on P. And then I'm going to write it like this. It's going to be a sum. So this, and I'll explain what this notation is. It's going to be a sum of the following things. So it's going to be the area of the lower rectangles. So first off, what is an area of a rectangle? So here, I'll draw the picture. Suppose this is our partition here. X naught, X1, X2, and X3, right? So if I take the lowest value that F takes on between X naught and X1, and I form this rectangle right here, I would like to know what its area is. So first off, the area of a rectangle is the product of its two side lengths, right? What is this side length right here? What is this side length right here? Can anyone tell me?
X1.
Just X1?
Times H.
Well, what is H? I want to know this length. What is this length? It's not an area. It's just a length, right?
The change of X.
Yes, the change of X, but the change of X between X1 and X naught, it's a difference, right? So what do I write? It's X1
minus X0. X0.
Exactly. X1 minus X0, or I say not. So the difference between X1 and X naught is this length right here, right? And similarly for can someone else tell me what this length is?
X2 minus X1.
Good. Right. Now, then there's a question of what about the height? What is this height? So remember that this is my function f. And then I'm, by the way, I'm going to introduce another piece. Okay, I am going to introduce a piece of notation here. If on some set X of F means inf of F of X. So in other words, this is the smallest value or the least, the greatest lower bound. It's the best lower bound that you have for the set of values that f takes on x. So if we consider inf from on the interval x naught to x1 of the function f, then that should be this height, right? So this height right here, it can be written as inf on the interval x naught to x1 of f. So how do you understand this? Well, if the function takes a bunch of values, then there should be and the function is bounded. So we're going to assume that f is bounded. Assume f is bounded. Bounded on L. Then there exists a height. And you should just think of this symbol as denoting the height. We need some symbol for the height, right? And so we introduced some machinery of lower bounds and best lower bounds. And this set of symbols just means the height of this rectangle. So then what is the area of this rectangle? What is the area?
X1 minus x0 times that.
Exactly. And now, in general, I want to sum up all of these areas, right? So this symbol right here, this is a summation. And so it means a sum of several things. So it's going to be a sum of x, let's say, I minus x sub I minus 1, inf on the interval from xi minus 1 to xi of the function f. And then this is a summation that ranges from I is equal to 1 to n. So this means the sum of all of these rectangles. This is precisely the sum of the areas of the rectangles. So for every single partition, we get this expression and it's written like this in notation. These are just symbols that mean the sum of areas corresponding to this partition, right? Now, similarly, I can define upper sums. And the difference between upper sums is now instead of an inf, I'll consider a sup. So in other words, I've defined for every partition of the interval, two numbers. The lower sum of f on p and the upper sum of f on p, right? So these are just two numbers. When I have a bounded function, I'm going to assume that f is bounded on some interval. And I have a partition, so I've specified how I'm going to chop the function up. Then I can take the sum of the lower areas and I can take the sum of the upper areas. Any questions about that? So I know I'm throwing a lot of notation at you, but this is just the way that in mathematics we write the sum of the lower rectangles and the sum of the upper rectangles. Okay, now I'm going to give you the definition of an integral. So the intuition is that if the integral from a to b of f of x dx is equal to k, in other words, if the area is k, then the lower sum of f on any partition is less than or equal to k, is less than or equal to the upper sum of f on any partition. So if the area exists, I don't know what the area is yet, but if the area exists, then it should be bounded on both sides by the lower sum and the upper sum, right? So we say the integral from a to b of f of x dx is equal to k if these bounds close in on k. So this is different from the definition in the notes. This is a slightly easier definition. So in particular, formally, integral from a to b of f of x dx is equal to k if there exists a sequence of partitions of partitions of L such that the limits on n of the lower sums of f on Pn is equal to the limits of the upper sums. So in other words, the upper bounds and the lower bounds close in on some specific number along some sequence of partitions. And of course, I'm going to give you, there are two homework problems about integrals. We already now have, how much time do I have? I have 20 minutes to do the calculations. So here are some results. So by the way, you should look at the notes. If we consider, for example, the sum from I is equal to 1 to n of the number I, then this is equal to n times n plus 1 over 2. So in other words, if I sum 1 plus 2 plus dot 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 plus n, this is equal to n times n plus 1 over 2, right? Now, what happens if I sum squares? If I sum 1 squared plus 2 squared plus dot 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 plus n squared, then this is just a formula. It's given in the notes. This is equal to n times n plus 1 times 2n plus 1 over 6. And in the notes, I also give a formula for cubes. So 1 cubed plus 2 cubed plus dot 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 plus n cubed is equal to n squared. It's actually the square of the first formula. Okay, so we have all of these things. Now I'm going to define a notion of uniform partitions. If if L is equal to AB, let's the nth uniform partition So in an uniform partition, we take n+1 points that are evenly spaced between A and B. If this is A to B, then the nth uniform partition looks like this. So this is x naught, this is xn, and then let's say we take 3 uniformly spaced points. All of these lengths are equal. P sub n is x naught less than xn for x sub I is equal to, well, we can say A plus the difference from B minus A over n times I. So this is how you get n points uniformly spaced from A to B. So n+1 uniformly spaced points from A to B. Does the notion of a uniform partition make sense? So these are evenly spaced points. Well, so very frequently when we look at these partitions, we're going to consider the uniform partitions. These partitions don't have to be uniform, but we can consider uniform partitions. So I'm now going to give you an example. Let's f of x is equal to x squared. Then the integral from 0 to 1 of x squared dx squared, sorry, dx is equal to 1/2. I'm now going to show you how you do this. I'm going to say, let's P sub n be the nth uniform partition of the interval 0, 1. So in other words, then P sub n is exactly the partition 0 is less than 1 over n is less than 2 over n is less than ... is less than n over n, right? So this is how I put n+1 uniformly spaced points between 0 and 1. Now, from calculus A, we know that f is increasing on the intervals 0 and 1. So let's just draw a picture. Drawing a picture is always good. If in the course of your proof, or sorry, I shouldn't say the word proof, if in the course of your solution, you draw a picture, that will make me happy. Drawing pictures always makes for more presentable work. So let's say this is 1, and let's say I take the third partition. So the third partition will have 4 endpoints and it'll have 3 subdivided intervals. Then if I look at what the upper sums are, so let's say I draw the upper sums. The maximum value will be given by the right endpoint because it's increasing, right? Does that make sense? So the maximum value, so sup on the interval xi to xi plus 1 of x squared is equal to the right endpoint squared because it's increasing, right? So now I consider what the upper sums are on the uniform partition. And I can write this as, well, remember what my partition is. My partition is this. So if I write this not as a sum, but just using the ellipsis, the dot, 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 then I can say that this is equal to 1 over n minus 0, right? Times the biggest value that f takes on this interval. Well, that's 1 over n squared. Then I can consider 2 over n minus 1 over n. And then I can consider the biggest value that it takes on this interval. Well, that's 2 over n squared, right? And then I can write a dot, dot, dot plus n over n minus n minus 1 over n times, now the biggest value it takes is n over n, which is 1. Now, if I look at this expression, and by the way, you're allowed to write dot, dot, dot in your work. That's fine. I don't require you to write sums. You can write dot, dot, dot. If I look at all of these, what's the difference? What is the difference between any two consecutive endpoints?
One over n.
Exactly. So this is equal to 1 over n times 1 over n squared plus 1 over n times 2 over n squared plus dot, dot, dot plus 1 over n times n over n squared. And another way to write this is that this is 1 over n cubed. There are 2 n's here and 1 n here, plus 2 squared over n cubed plus dot, dot, dot plus n squared over n cubed. Oh, I finally exhausted the space. And then I can factor out the 1 over n cubed. And then I get that this is 1 squared. I can write a squared here as well. Plus 2 squared plus dot, dot, dot plus n squared. And then I look at the notes and I have a formula for this. The sum of squares is this. So this is 1 over n cubed times, and then I just look at the notes and I look at the formula that I have, because I know that this formula is going to come up in this problem. N times n plus 1 times 2n plus 1 over 6. And then I can divide through by n cubed. And I can write this as, well, I guess n over n times 1 plus 1 over n times 2 plus 1 over n over 6. So I've divided top and bottom by n cubed, and then I've given an n to each factor. And I can just write this as 1 plus 1 over n times 2 plus 1 over n over 6. So in other words, I've taken this uniform partition and I've calculated what the upper sum is on the uniform partition by knowing that the supremum is given by the value on the right endpoint. Any questions about this calculation? So remember, if, for example, go
I have
ahead.
a quick question. So could you so like the third part before your final answer, could you like FOIL everything out and then distribute the n and then cancel out the ends?
Right. So what that would give you is the same thing as if I distributed it.
Okay.
Yeah, that works. But remember that if we're taking the limit of this, you can distribute limits over multiplication.
Right. Okay.
So you can save yourself the trouble of having to FOIL. But yeah, you could distribute this if you wanted to. That's also fine. So remember that, for example, if n is equal to 3, and this is just the function x squared, then what are we doing? I can actually give you a number for this. Then this endpoint is 1/3. This is 2/3, right? And then we want to sum the area of these 3 rectangles. So the upper sum of f on P3 is going to equal 1/3. Then we're going to have three areas, 1 squared plus 2 squared plus 3 squared. And well, I can actually calculate what that is. 3 squared is, so it's going to be 9 plus 4 plus 1. Well, that's 13, 14, so 14/3. Sorry, this is, it's not 1/3, it's these divided by 3 squared. So yes, so it's going to be 14 divided by 27. So in other words, if I subdivide it into 3 pieces, then I get the number 14 divided by 27. And that's bigger than 1/2, right? Because 14 times 2 is 28. So I get something that's just a bit bigger than 1/2. We want to show that the upper sums go to 1/2. Well, before, when I was talking about limits of sequences, we now have limit laws. Well, the limits of the upper sums of f on P sub n as n goes to infinity. Well, I typically don't write n equals infinity. I'll just write the limit on n. Well, what's that equal to? Well, that's the limits on n of this expression. I can distribute the limit inside. I can write this as, I guess, 1 plus limits on n of 1/n. 2 plus limits on n of 1/n over 6. And then that's 1 plus 0 times 2 plus 0 over 6. And that's equal to, well, 2/6 is 1/3. Yes, sorry, this is bad. I forgot. Everyone should have corrected me. It's 1/3. It's not 1/2. It's 1/3. Of course, it's 1/3. We've done some integrals in high school, so we know it's 1/3. Yes, bad mistake on my end. In the notes, did I write 1/3? I hope I don't make this mistake there. No, good. In the notes, it's 1/3. Good, good, good. Anyway, so that's the upper sum. Now, what about the lower sum? Well, the lower sum, instead of taking this endpoint, we take the right endpoint. So if you do a calculation, you can find that the lower sum, so you find, just by doing this calculation, that the lower sum is going to be given by 1 minus 1/n. So check the notes for the details. 2 minus 1/n over 6. And then you can find that the limits on n of the lower sums of f of P sub n across these uniform partition is also 1/3. And so by explicitly calculating the upper sums and the lower sums and taking the limits along the sequence of partitions, we find that the function is integrable. And that the integral is 1/3. So what this calculation required is explicitly setting up these sums and explicitly summing it. So now we finally get to the question on the next question on the homework. And this is question number 6. So question number 6 asks you to find the integral from 0 to 1 of x cubed dx. So here we did x squared, but now you're supposed to find x cubed. So for the upper sums, you similarly take the endpoint, except for instead of being 1/n squared, it's going to be 1/n cubed, right? Does everyone see that? So the difference between the calculation for of x cubed and x squared is that instead of having these x squareds here, we're going to have x cubes. And the formula that we're going to have is not the formula for a sum of squares, but it's going to be the formula for a sum of cubes. And I give that to you. So the homework problem 6 asks you to just to imitate this calculation. It's basically the same calculation, except you use a different formula here. Instead of squares, you use cubes. And again, how do you write this up? Well, look at how I wrote it up. Look at how I wrote it up. I said, let P sub n be the nth uniform partition. So I'm telling you explicitly what my P sub n is, and then I'm also giving you an expression for the endpoints of P sub n, right? Then I tell you what the upper sum is, and I justify why I'm taking the right endpoints. I'm taking the right endpoints because f is increasing on 0, 1, and the function x cubed is also increasing on 0, 1. Then I write down an expression for the upper sum. If I look at what the definition of the upper sum is, then this matches that definition. It's the difference between consecutive endpoints times the maximum value that f takes on that interval, with the better souped up version of max. Then I notice that all the differences are 1 over n because it's the uniform partition. That's the main point of the uniform partition. And then I group the maximum values. I distribute the squared over each one of these terms. I group these n's to an n cubed. It'll be n4 on your homework. And then I use the formula, and then I cancel out and I get a formula. And then I take the limits of the upper sums, and then I use limit laws and I get something. And then I do the same calculation for the lower sums. So here I'm running out of time, so I just told you what the calculation is, but on the homework, you'll have to do this calculation twice, and you'll have to give the lower sums, and then you'll have to give the same argument that the limit is also that value for whatever value it is. So I'm not going to tell you what value it is. You should just write out what the upper sums are and the lower sums are and take the limits, and you'll find what the value is. And so that explains the 6th homework problem. It's not actually a hard homework problem if you just mirror exactly what I did, replacing the squares with cubes. Does that sound okay? Again, the way that you're supposed to approach this homework problem is you go to the notes and you look at this calculation, or you rewatch this lecture and you go through this calculation. So it was very important that we did that calculation. And finally, okay, I have 8 minutes. You know, that's generous. I'll tell you about the last homework problem. For the last homework problem, consider the function. It's going to be a discontinuous function. So it's going to have a piecewise definition. Sometimes it's 0, sometimes it's 1. It's 0 when x is less than 1/2. And it's 1 when x is greater than or equal to 1/2. So if we were to graph this function, it looks like this. So here is 1/2. So it's 0 here, and then it has a hole here, and then it's 1 from here. So let's then consider the interval defined on the interval 0, 1. So the question is to find the integral from 0 to 1 of f of x dx. And in general, what happens is that if you divide your partition into some number of pieces, let's say 3 pieces like this, then the lower sum and the upper sum, well, these rectangles, the function is constant. So their area does not change between the lower and the upper sum, right? But as for this rectangle that contains this point in the middle, the upper sums and the lower sums jump. The upper sums will look like this. The upper will have 1 and the lower sum will have inf. So if 1/2 is in the interval x1 to x2, then sup of on x1 to x2 of f is equal to 1, and the inf on x1 to x2 of f is equal to 0. Because let's say if it's in this open interval, if it also includes technically you could just, sorry, let's say it like this. If it's properly inside, because I could just take 1/2 to the next endpoint. But anyway, we suffer a problem either way. Actually, you know what? I can make it even, well, this is a true statement, but I can even do this. This is also a true statement. Anyway, it doesn't matter. The point is, if this point is properly inside some interval, then the sup and the inf jump on that interval, right? So I tell you in the hints to consider the partition P sub n is the partition 0 is less than 1/2 minus 1 over n, is less than 1/2 plus 1 over n, is less than 1. And then you're supposed to calculate the lower sums on this partition and the upper sums on this partition and show that they converge to the same value. Now, it's sort of clear what that value is. What's the value of the integral? Can someone tell me? So this value is 1, and we have a rectangle that's half as long. So this is 1/2 times 1. What does that give me?
1/2.
Yeah. So the answer should be 1/2, right? Because it looks like this. The problem is that so here's the interesting thing. The partition P sub n is equal to just 0 to 1/2 to 1 does not work. And the reason it doesn't work is that on the interval, it's because on 0 to 1/2, inf and sup jump. Because you're including this endpoint, and there's just one point in that interval. And the fact that that one point is included in the jump. So if you try and sum over these partitions, it will fail. So you have to work with these partitions. Well, there are other partitions that you can consider, but I think these are the best to work with. So that covers problem 7. It's not a very hard problem because you just consider this partition of 3 pieces and you realize that it jumps in the middle. Then you write the upper sums, then you write the lower sums, and then you use limit laws to show that the limit across these partitions P sub n, they goes to 1/2 from both sides. So I have today told you how to solve every single homework problem. I will send you, so I have to do some things. Apparently you need passwords to access the lectures, so I'll send you those passwords, and I'll send you instructions for submitting the homework. Although you shouldn't worry about the instructions for submitting the homework for today or tomorrow because you need to actually do the homework. So do it on paper, or if you can do it on the computer using like writing, or if you want to type it up even better, like in my notes, that's better. I prefer that. But for now, you should solve the problems, and I'll send you right after this passwords. Actually, I won't send it to you right after. It takes about an hour to produce the password for this lecture. When that password is produced, I'll send it to you. And then you can go through this, and I numbered every single problem, and then you go through it. And so I want you to have good write-ups. So please try and spend like an hour on each problem and make the write-up as good as you possibly can. I'm going to scrutinize this very intensely. And then finally, let me just review what the notion was. So for integrals, that's the most important definition this week. You also have, I'm going to give you another piece of homework for next week, and that's to understand this definition of integral. It's very important that you understand the definition. So what's the definition? The definition is we take a function, we take a partition, which is just a way to cut up this interval. We form the lower sums, we form the upper sums. These are things that the area has to lie between the upper and the lower sum. Well, okay, I need to tell you one more thing. So not every function is integrable. Let's f of x, this is the classical function, equal 0 or 1 if x is a rational number and otherwise. So this function is 1 on every irrational number and 0 on every rational number. I can't draw the graph of this function. It basically looks like, well, there are a bunch of rational numbers and there are a bunch of irrational numbers. And these are everywhere. The problem is that any interval of positive length have both rational and irrational numbers. So all of the upper sums, so for any p in delta I can tell you what the upper sums and lower sums are. Upper sum of f on p, so all of the supremums are going to be 1, so this is just going to be 1, and the lower sums of f on p, well, all of the infimums are going to be 0. So no matter how you slice it up, all of the upper sums are 1 and all of the lower sums are 0. And you can never get those two things to close in on each other. There's always going to be a gap between where they happen. So the function, this function is not integrable. And that's surprising. So there exist functions which cannot be integrated. In other words, this function is very pathological. It's very oddly behaved. This is an incredibly not continuous function, and we can't integrate it. This is also a function that's not continuous, but it can be integrated. But this function is horribly, terribly discontinuous. And sort of if the discontinuity is completely unmanageable, it can happen that functions no longer become integrable. In other words, there's no meaningful way to assign the area under the curve under this notion of integration. And then there's another notion of integration, which you can learn in advanced pure mathematics classes, called Lebesgue integration. And this function becomes Lebesgue integrable. But there are functions which even can't be Lebesgue integrated. You can make even more terrible sets. One of those sets is called the Vitali set. It's non-measurable set. So there's no notion of integration which can integrate that. But for now, we're just working with this notion of integration that's called Riemann integrability. And here's a function that's not Riemann integrable. So I hope that's interesting. But we're going to discuss what can be integrated next time. And I've gone over all of the homework problems. Are there any questions? Was today more understandable than last time? Oh, by the way, if anyone wants to have office hours with me, you can send me an email and I can just meet you at your convenience. Or then also, you're not allowed to post questions directly about the homework on Piazza, but if you have any questions about the course material, please start posting on Piazza. I want people to start using Piazza. Come on, some Piazza posts, please. Right, okay, sounds good. Can anyone say anything? So are we good?
Yes, I appreciate you breaking everything down. Thank you.
Okay, good. Okay, see you next Tuesday, and I will send you instructions for how to submit the homework. And the homework needs to be submitted before the start of next lecture, following the instructions that I sent. And if you did not get an email from, yes, thanks, on the mailing list, then send me an email because you're not on the mailing list. So if you do not get an email about an hour and a half before the start of lecture, send me an email. Okay. See you on Tuesday.
Thank you so much. Have a good weekend.
Likewise.
Thank you.
Thanks. Bye.